This is AP Calculus 8.2, connecting position, velocity, and acceleration of functions using integrals. And we're just going to review the position, velocity, and acceleration of functions and then work our way backwards. They might give us acceleration and we will work our way back and find the position function using ordered pairs that they gave us by finding the particular solution. A notation for the position function is P of t. Sometimes they use X of t. Sometimes they use S of t. And they represent a location of an object at a specific time. So if they mention something like P of 2 equals 10, what that would mean is at time 2, whether it's seconds, hours, minutes, whatever it is, then the object is 10 feet from the starting position. The velocity, which is the derivative of the position function, can be notated as V of t, P prime of t, X prime of t, or S prime of t. All of those are common representations. And the velocity function represents the speed the particle is moving at time t. So if it has like V of 2 equals negative 15, that means at 2 seconds or 2 minutes, whatever the time unit is, the object is moving negative 15 feet per second or per minute, whatever the time unit is. And if it's a negative, that means it's either moving left or falling. If it's a positive, that means the velocity is moving toward the right or up. And the absolute value of the velocity is your actual speed, because we know speed can't be negative. So if we take the absolute value of a negative velocity, we'll have the actual speed of the object. So an object that is falling, like if you drop a ball from a balcony, that object is falling, so its velocity will be negative, but its speed is positive because speed can't be negative. And then the acceleration function, A of t is a common use for that. That is the second derivative of the position function, or the first derivative of the velocity function. So A of t is P double prime of t, X double prime of t, S double prime of t, and it represents the rate of change of the velocity. And if acceleration is positive, the particle is speeding up. If acceleration is negative, the particle is slowing down. The displacement, or the distance traveled by a particle over a time interval AB, which is a closed interval. The net distance traveled over the interval AB is the integral from A to B of the velocity function. The total distance traveled over a time interval AB is the integral from A to B of the absolute value of V of t dt. And you need to understand the difference between these two things. So let's talk about the difference between these two. If you talk about net distance versus total distance, it's very similar to your paycheck. Your net amount that you bring home is the amount you bring home after taxes. It's not how much you made, it's how much you bring home after taxes. The gross income that you make is what you make over all your total salary before taxes have been taken out. You can think of net distance and total distance traveled similar to that. Your net distance is just the distance something is from the starting point. So you could start out somewhere, like let's just say you start out right here, and let's say you travel this far in 2 minutes, and then at the 2-minute mark you go back this direction and you end up right here at the 3-minute mark, and then you end up here at the 3.5-minute mark. Well, your net distance traveled is this distance right here, where you are in terms of where you started. That would be considered your net distance. It does not take into account that you went all the way over here and then back again and then back again. It doesn't take any of that extra motion into account. All it's going to account for is where you are compared to where you started. That's your net distance traveled. Your total distance traveled would be if we added up all of these distances together to get your total distance. So that's the difference between these two. So how does this look in terms of a graph? Well, remember when we talked about the area between the curve and the x-axis, we said that anything on top is considered a positive area and anything on bottom is considered a negative area. So basically here your net distance would be the positive area minus your negative area, or 12 minus 2, and that would equal 10 for your net distance. But for your your total distance, we're taking the absolute value of these things. And so we would have the absolute value of 12 plus the absolute value of 2, giving us a total of 14. So it doesn't take into account what part was negative and what part was positive. It's just the total distance there. The next thing we need to talk about is that final position of a particle. If you go back to the formulas, notice here the net distance traveled is the integral from a to b of v of t dt. And the total distance traveled is the integral from a to b of the absolute value of v of t dt. The next thing we need to talk about is the final position of a particle. And that takes into account where you started. So S sub a is going to be our initial position. We could also call that S sub 0 or S of 0. If we add where we started to our net distance traveled, we'll have where we ended up. And if you think about that, wouldn't that have to happen? Because if we start somewhere, regardless of how far we go in either direction, where we end up is going to give us our final position. So if you think about it this way, Jan leaves her house to see her friend Sam, but needs to fill her car with gas first. Jan leaves her house, gets gas, and then travels to Sam's house. Find the following: Jan's total distance traveled and Jan's final position. Well, she's starting at her house, so that is our starting point. So she's leaving her house and traveling to the gas station, and we know that distance is 3 miles. After she gets gas, she's then leaving the gas station and traveling all the way over here to Sam's house. So if we're looking for her total distance traveled and her final position, those are two very different things. If we're thinking about her total distance traveled, this is her initial position. We'll call that 0. For her total distance, she's traveling 3 miles this way and then 5 miles to get to Sam's house. So 3 plus 5 would be a total of 8 miles traveled. But her final position is going to be, she started at 0 and ended up at 2 miles. So her final position will be 2 miles. We get that final position by just taking the difference of the distances from where she started to where she ended up. And if you think about that, that makes sense. If this is her net distance plus her starting point would give us where she ends up at the end of the problem. So this brings us to position, velocity, and acceleration. Back in one of the first units of study that we did, we talked about the position of a particle that moves along a straight line. And we said that the position function of that particle in feet per second or feet per minute, depending on the unit of measure, depends on the problem. But we said a basic formula for position was going to be -16 t squared plus v sub 0 of t plus s sub 0, where v sub 0 and s sub 0 were the initial velocity and the initial position. And then we said that if that is in meters, instead of having a -16 in front, we would have a -4.9, and that would be a -4.9 t squared plus v sub 0 of t plus s sub 0, where v sub 0 and s sub 0 are still your initial velocity and your initial height. And why do we have a -16 and a -4.9? Well, that's because we're on Earth. The gravity on Earth would cause our position functions to be a -16 for feet and a -4.9 as a coefficient for meters. If this problem were taking place on the moon, then the numbers in front of your t-squared would be different. Now, we don't need to get into all that. All the problems that we're going to talk about are going to be on Earth, but you need to understand that if they take you to another planet for some sort of a word problem, you would have to know what these new numbers are for that specific planet or the moon or wherever it is that you're going. So we're going to look at this, and we're just going to figure out, based on this information, how to work backwards to get our P of t function. Now, this one is in feet per second. It tells us that in the reading. So we know we're going to use this model. If this were meters per second, then we would use the second model, okay? So a ball is thrown vertically upward from an initial height of 80 feet at an initial velocity of 64 feet per second. How high will the ball go? At what time will the ball reach its maximum height? And when will the ball hit the ground? Okay, if you think about this, they're not giving us really a whole lot of information about acceleration. But what we need to understand is our initial velocity here is 64 feet per second, and our initial height is 80 feet per second. So couldn't we just plug the 64 directly into the function for v sub 0? And couldn't we just plug in the height for s sub 0 of 80 and have our equation that we're looking for? Now, why does this work? Well, they've basically given you two ordered pairs. They've given us that the initial height is 80. So what that means is s of 0 is 80. And they've given us an initial velocity of 64. What that means is v sub 0 is 64. So what I'm going to do is I'm going to work backwards to show you why it is okay to just plug these values in here. I'm going to show you where this comes from. Now, if you think about this, we know that velocity is the derivative of the position function and acceleration is the derivative of the velocity function. Don't we know that if we find the velocity of this, our v of t function is going to be negative 32t plus v sub 0 if we do the derivative. This is going to drop out and our t is going to drop out. And then if we then do the acceleration function, wouldn't the acceleration of that, no matter what these numbers are, always be negative 32, as long as we're on Earth and we're dealing with feet per second, or dealing with the unit measure of feet? Well, if that's the case, then couldn't we say, okay, to get the velocity function, I'm going to take the antiderivative of this. So I'm going to take the antiderivative of acceleration to get my velocity function. So if I take the antiderivative of this, that would give me v of t. And remember, since we don't know what this is, we always have to have a plus c. And then in order to find the particular solution here, we would have to be able to plug something in to find c. Well, they gave us an initial velocity. So at time 0, the initial velocity is 64. If I plug 0 in for t, I'd get 0 here. If I plug 64 in for v of t, wouldn't that give me 64 is equal to c? Knowing that, I know that my velocity function is negative 32t plus 64. So the position function is the antiderivative of the velocity function. So if I take the antiderivative of this, I'll have negative 16t squared plus 64t plus c. And then we were given the initial condition that s of 0 equals 80. So if I plug 0 in for t and 80 in for p of t, or in this case, I really should have used s of t since this was talking about well, since that's what I used here, I guess it doesn't really matter. I could change this to p. I could change that to p of 0, and it's fine. So p of 0 is 80, so I'll have 80 equals c, because if t is 0, these drop out. So my position function then becomes p of t equals negative 16t squared plus 64t plus 80. So this is the position function that I have worked my way to by doing the antiderivatives of the acceleration and velocity functions. Now, how high will the ball go, and at what time will the ball reach its maximum height, and when will the ball hit the ground? Those are the questions that we need to answer. So I'm going to clear the screen here and just keep my position function, and then we're going to answer these questions. So if we're looking for how high will the ball go, well, if you think about that, don't we need to know when the velocity is 0? In other words, when the horizontal tangent line of this function is 0. Now, if you think about what this function would look like, wouldn't its graph be a parabola that's facing down, something like this? And at whatever time it is that we have a horizontal tangent line, that's where this function is reaching its maximum height. So the function will reach its maximum height wherever this happens. Well, if we're trying to figure that out, isn't that where the velocity function will be equal to 0? So if we think about back to the velocity function, if we set that velocity function equal to 0, we'll be able to figure out at what time this happens. So at time t equals 2, the velocity is 0, and that's where this thing will reach its maximum height. So when it says how high will the ball go, we just need to figure out what is the position of this function at t equals 2. That's when the velocity is 0, which is where it's at its highest point. And so that's the time we plug into the position function to find out how high, or its position, at that moment in time. So we're finding p of 2. And p of 2 is 144 feet. So the maximum height is 144 feet. And then it says, at what time will the ball reach its maximum height? Well, that we already found. That's t equals 2, and we should say seconds. And when will the ball hit the ground? Well, if you think about where the ball will be when it hits the ground, if this is where the ground is, okay, don't we want to know what time this happens? We know that the initial height is at 80, which I would say is maybe around right here. somewhere. Okay, so that's our initial height. So we want to know how long it takes this ball to travel from there to when it hits the ground. So what is the position when it hits the ground? Well, the position is 0. So if they're asking us when will the ball hit the ground, if we set the position function equal to 0, we will be able to figure out what time that happens. So that's what I'm going to do next. So if I set the position function equal to 0, I'm going to divide everything by -16. That leaves me with a really simple function that's easy to factor. So if I factor that, at t equals 5, that's when the ball will hit the ground. T equals -1 is when it was on the ground before. Well, if you think about time being negative, that can't happen. But our initial position of this function was at 80, so it never does travel here. The start of the problem is right here. So this portion of the parabola doesn't really exist. So at time t equals 5, and we should say seconds, the ball will hit the ground. For the next one, a particle moves along the x-axis so that the acceleration at any time t is given by a of t equals 6t minus 18. At time t equals 0, the velocity of the particle is 24 feet per second. At time t equals 1, the position of the particle is at 20 feet. So they've given us three things here. They gave us the acceleration function. And notice this one is not just at -32 feet per second. They've given us an actual equation for acceleration. It's not always going to follow that exact position function that we talked about in the last screen. Sometimes it'll have its own acceleration, position, and velocity functions. So they give us the acceleration function. We will use that to find what they're asking us to find. So we have the acceleration function. They've said at time t equals 0, the velocity of the particle is 24 feet. So that's actually an ordered pair. V of 0 equals 24 feet per second. Now, so this is our initial velocity. But since this a of t was not just -32, we can't plug this in for v sub 0 in the generic equation for velocity. We have to take the antiderivative of this to figure out what the actual velocity is for this situation and then plug this in to find our c value. And then the next thing they gave us was that at time t equals 1, the position of the particle is 20 feet. So p of 1 equals 20. So we're going to use this information to find everything they ask us to find. Here it says, write an expression for the velocity, v of t, of the particle at time t. Well, we know that the velocity is the antiderivative of acceleration. They gave us acceleration. So if I'm finding the velocity function, I'm going to take the antiderivative of that acceleration function. So v of t equals the antiderivative of 6t minus 18 dt. That dt is there because that's the variable of integration. They said a of t. They told us that here. That's why we need the dt. And so if I take the antiderivative of that, I will have 3t squared minus 18t plus c. Then I'm going to plug v sub 0 equals 24. So v of t is 24 when t is 0. So if I plug 0 in for these, that leaves me with c over here. So that means c equals 24, leaving us with the velocity function. V of t equals 3t squared minus 18t plus 24. That is the expression for the velocity function at any time t, so we have done part A. Part B says, for what value of t is the particle at rest? Well, our particle is at rest when the speed is 0. The speed is 0 when the velocity is equal to 0. So we're going to set the velocity function equal to 0 and solve. So this is just a simple factoring problem. I'm going to divide everything by 3 and then factor. So this particle is at rest at 4 seconds and at 2 seconds. We've answered part B. Then it says, write an expression for the position p of t of the particle at any time t. So we're writing the position function. Well, we know the position function is the antiderivative of the velocity function. So if I take my velocity function and take its antiderivative, I will have the position function. So here's the setup for that. P of t equals the antiderivative of 3t squared minus 18t plus 24 dt. If I take the antiderivative, I will end up with the following. So when I take the antiderivative, I get p of t equals t cubed minus 9t squared plus 24x plus c. Then I can plug in this ordered pair and figure out what c is. So if I do that, then I can plug in the p of 1 equals 20 into this function and solve. So p of t is 20, and then when I plug 1 in for all the t values, I will have 1 minus 9 plus 24 plus c. So this gives me 20 equals 16 plus c. If I move the 16 to the other side, I end up with 4 equals c. So my c value is 4, leaving me with a p of t value, t cubed minus 9t squared plus 24x plus 4. So this is my position function. We have answered part C. And then the last thing they ask us to do is find the total distance traveled by the particle from t equals 1 to t equals 3 seconds. Okay, this becomes important because if you think about the information that we have for this problem so far, we know that if we're traveling from time t equals 1 to t equals 3, first of all, we need to know where this thing is at t equals 1, and we need to know where it is at t equals 3. But it's not quite that simple. That's a common mistake, is people try to subtract those two things and get your answer. But wouldn't that just be your net answer? It's not going to be the total distance traveled, which is what they're asking us to find here. We know that this particle stops between t equals 1 and t equals 3. That's at t equals 2 seconds. And since this particle is traveling along the x-axis, we know that it is stopping, and then when it stops, it starts moving again. So that actual at time t equals 2 is a place where it stops and then changes direction. So we have to account for that when we're finding the total distance traveled. So what I'm going to do is I'm going to use this function right here, our position function, and then I'm going to use the information I'm getting here at the time t equals 2 seconds to figure out where exactly this particle is at 2 seconds, how far it's gone, and then we'll add all our different distances together. So let me make some room here. I don't know if you noticed it or not earlier, but I had over here 24x instead of t. That my variables should all have been t's. That was just a force of habit. So, okay, so I need to figure out the position at 1 and the position at 3, and then the position at 2 to determine how far this thing has moved in the opposite direction before ending up where it ended up. So my p of 1, p of 3, and p of 2 are my significant values. So here are those positions. Well, p of 1 was given to us. P of 1 is 20. They gave us that in the reading. Okay. P of 2, I plugged 2 in here. I got 24. P of 3, I plugged 3 into this. I got 22. So if we're thinking about where this thing is, at P of 1, it's at 20. Then at P of 2, it's traveled all the way up here to 24. And then it stopped and went backwards and ended up at 22. Well, 22 would be halfway, but so if we're considering our total distance here, it went 4 and then 2 more. So our total distance would be 6 feet as our total distance traveled, and we have answered D.